Yes.
Hello?
Great.
Can I try to?
I did make you
The microphone was mute, so
Let's check. Hello, hello. It seems okay.
Yeah.
yeah.
Ah, okay.
Now,
that's
now
okay.
I think now it's okay.
No, that should be okay. It
Yeah.
should be okay.
Yes, but okay.
Thank you.
You're welcome.
I
Go ahead.
read my presentation. Okay, thank you. Good morning. My name is Francisco Santos. I'm a PhD student at the University of Minho, and I present this work developed in collaboration with my supervisors, Professor Lino Costa and Professor Leonildo Varela. These are an overview of this presentation. I will begin by explaining the motivation behind this study. Next, I will describe the problems and the model we propose, followed by the problems objectives, the experimental setup, and the results. Finally, I will present our main conclusion and outlay direction for future research. Traditionally, job shop scheduling considers single manufacturing units. Distributed production not only increase production capacity, but also bring production close to consumer market, reduce logistic cost, and mitigate risk associated with localization strategy. Wherever this decentralized introduce additionally complexities in production, planning, and control, particularly about the coordination of job between different manufacturing units. Meeting delivery deadline has become a key competitive advantage, involve not only minimize deadline, but also reduce production advancement. This work proposed a multi-objective model for the distributed job shop scheduling problem that incorporate unrelated parallel machines, sequence-dependent setup times, raw material transport time, and customer order delivery time. We are dealing with distributed job shop scheduling problem, which involve multi-factors. Each factor has its own set of machines. There are set of jobs that need to assign to machines. Each factory consists of several unrelated parallel machines and handling a subset of the job. So the scheduling objective is to assign jobs to machines and determine the processing sequence of job that minimize one or more objectives. The data are the processing time, sequence-dependent setup time, transportation time between factories, and delivery dates. This slide shows how jobs are scheduling across factories over time. Each bar represents a machine with factory, and the blue blocks correspond to jobs. For example, we can see the sequence of jobs in machine in factory 1 to factory F. This scheduling account for the processing time, the setup time, and transportation time. The core challenge here is to determine the best combination of job assignment, deciding which factory and machine will process each jobs. The goal is to achieve optimal or near optimal performance across multiple objectives. Here, we illustrate the completion time of jobs across different factories and machines that are crucial for evaluating performance metrics such as max span, the maximum completion time among all machine and factories such as tardiness and earliness. The tardiness time for a given sequence is given by this expression T max. Here, the tardiness is computed involving the completion time of the jobs. For example, the green line represents the due date. D3 indicate a tardiness since the job 3 ended later than the due date. The earliness for a given sequence is defined by L max, which is related by the difference between the due date and the completion time for job. In this figure, we can see earliness represented by the yellow line. Job D2 is an example of the earliness because it finished before the scheduled deliver date. To this end, 3 problems with several objectives were defined. F1 to minimize max span and tardiness, F2 to minimize max span and earliness, and finally F3 with simultaneously minimize all the 3 objectives. To test this approach, 3 instances taken from a previous study were used applying the NSGA tree. The implementation was carried out in Python using the Pymon framework. The population size was set to 100 and 200 chromosomes for B objective and 3 objective respectively. And 20 independent runs were conducted for each instance and problem. This slide presents the Pareto front obtained by solving the F1 problem. For instance, P1 to minimize max span and tardiness. 2 non-dominant solutions were obtained. Solution A1 is better than solution B1 in terms of max span, but worse in terms of tardiness. In fact, solution A1 has a tardiness value greater than zero, with means that the deliver date to customer for the job are not fully met. On the other hand, solution B1 meets all deliver date. The Gantt chart above represents solution 1. Not all jobs are completed by the scheduling date. Solution B meets all deliver date for the deadline for the customers. Thus, it is a good solution from the perspective of customer requirement. For problem F2, which consists of minimize max span and earliness, 4 non-dominant solutions were found. Solution B2 and C2 lie at the inflection point of the Pareto front and may represent good trade-off between the 2 objectives. Solution D2 has zero earliness, meaning that all job finish exactly of the customer's delivery date, but with a long max span. The results of problem F1 and F2 show how important it is to consider max span, tardiness, and earliness at the same time. So this figure shows the approximation of the Pareto front obtained for problem F3. In this figure, max span, tardiness, and earliness time are represented on the x-axis, the y-axis, and by the size of the point, respectively. It, it can be observed that, in general, total max span and earliness are negatively correlated. That is, a max span increase, earliness then tend to decrease. This behind does not occur with tardiness. These results confirm the contradictory nature of these three objectives. These are the result of instance P2. 11 non-dominated solutions were found. It should be noted that there is no solution with tardiness equal to zero. That is, the customer's delivery date cannot be all satisfied simultaneously. The solution with the smallest tardiness has a delay of 24 solution B. No solution has found with earliness equal to zero. However, solution K has an early value very small. These are the results of problem F3 for the instance P3. The Pareto optimal front has 16 non-dominated solutions. Solution A, D, and P are the solution with extreme value of the objectives. For this instance, the solution D has the tardiness equal to zero. The earliness to solution P is 0.2. The main conclusion of this study is incorporation of customer preference into the model achieved through the simultaneously optimization of three fundamental objectives: minimize of max span, tardiness, and earliness. It was observed that minimize the max span may lead to minimize deadline, while strict compliance with delivery date may require an increase in total production time. On the other hand, minimize earliness can help reduce costs associated with customer inventory. As future work, we intend to extend this study to larger and more complex systems, and will has to explore the incorporate of additional objectives. Finally, compare the performance of NSGA3 with other multi-objective meta heuristics. And these are the reference, and thank you very much.
Any questions? Go ahead.
I have one question. Maybe I can see the execution time. How much does the algorithm takes to execute one?
We not register the time of the execute the algorithm, because we have the small data, and I think it's not important for, yeah, it's very fast for execute, but I we when where if we need more data, we can try to resist the time. Yeah.
Thank you. Any other questions? You can do the questions afterwards in copyright. So thank you again for speaking. And we move to the third presenter, which is Film Pink. Go ahead. I forgot to tell you have water if you need.
Thank you. Not like that. Okay, now it's working. My intention was to use our app of ICCSA, the presentations of Damiano Perry, but I'm not convinced that it will work. Let's see. Okay, let's see now. It's working. Okay.
You see, you're doing the elegant way. You're following the instructions. You are moving away from the camera. We'll leave you.
Okay.
Joking.
I will try to.
You're safe over there. You're safe.
Okay, I will try to put myself right in the camera. So, good morning again. My intention today is to present you a work of our Master Science student, Anaís Luz Silva, which was supervised by me and Claudio Alves from Algoritmi University of Minho. This work is about making scheduling, personal scheduling in call centers, but it's not. It's more than that. It's more than a combinatorial optimization problem. It's trying to do something that Anish wanted to do in the company, which is try to improve the feeling of being fair, the fairness considerations that we'll see in this presentation. So it's more than making just simple arrangements of people in shifts. As we know, personal scheduling has a direct impact in financial performance. Everyone here has experienced, some of them are good, some of them are not, with call centers. What we know is it is clear that if it is not, if the call center has not an adequate process of scheduling, we'll have increased waiting time, we'll have dissatisfaction with customers, but also we'll have dissatisfaction with our employees. And having employees having not good performance in the in the employee satisfaction can lead to several problems. So we are always trying to move persons to our company, but they want to go out because they don't seem motivated. In this organization, which is a Portuguese company, I can say that, I cannot write the name of the company, but I can say to you that it's a Portuguese company. That scheduling was made in spreadsheets, in Excel, manually, each 2 weeks. So it is a process that consumes a lot of time and consumes a lot of resources. Call centers are very important. Why? Because they are the first interaction that we have with some companies. Long waiting times, which is related to bad personal scheduling, can reduce the customer satisfaction and can have a direct impact in our incomes. We want to have call centers that are with good personal scaling because we can have cost efficiency and we can have more than that, trying to motivate our teams in these call centers can have a direct impact in our incomes. Why it is important at this moment? What it is important at this moment is to have decision support tools that can do this work automatically and very fast and trying to improve some metric. In this case, our company operates 24 hours a day, 7 days a week. As I say to you, it was made manually. Here we say that is monthly basis, but sometimes we have to do twice at each 2 weeks. And our objective is to develop a heuristic that produces high quality in a very fast way. In this point, we'll have to manage or try to schedule 1 month for our scheduling, divided in 2 periods. Why? Because company want to have teams working in a given way for each 2 weeks. So it changes each 2 weeks in a month. That means twice a month. We'll have 48 shifts, so meaning that each 30 minutes we have a different shift. And we'll have shifts of 9 consecutive hours, including a break in the middle as Portuguese law recommends. The company operates, as I said, 7 days a week and 7 days a week and 45 hours a day. Why? Because it is a company that serves from Japan to the United States. Our teams are organized in 7 different teams. I can say I cannot write some things because they are not to be said in public, but in this case I can say that teams are related to the language. So Portuguese team, English team, French team, and so on. Across 2 different cities in the north of Portugal. Each employee must have at least 11 hours of rest between shifts, as the Portuguese law recommends. Employees may work at most 5 consecutive years. Sorry, more than 5 consecutive years. Employee may work at most 5 consecutive days, and must after that must rest twice, 2 days, have 2 days off. And we want to maximize the number of times each employee remains assigned to the same work shift, because we discovered that there are a lot of employees not working. So in a month they have kind of 10 days of not working. Everyone wants to not work 10 days in a month, but it's not possible. This company is not sustainable. A second objective is to reduce disparities. Why? Because if some employees are resting 10 days in a month, other employees are not resting. So we want to reduce these disparities. And just to say to you that it was very surprise for us. It was when we were at this company, the process is made, how can I say, in a spreadsheet, but without any rationale. So we go at, okay, person 1 makes that, and I put in Excel and make this for all employees in the company that is very big. So it's not sustainable for this problem. Just a solution presentation to say in image that I want, something that I want to say to you in words. It is a kind of, it's a possible schedule. So in A, we have an employee that works 5 consecutive days, not years, and the rest at Saturday and Sunday. Here we have employee B that works Monday, Tuesday, rests at Sunday, but is not assigned to any shift in Wednesday. Note that at this point, the employee B is paid to be at home. Why? Because this one is the rest day. So we have a lot of these cases when we arrive at the company and we try to reduce that. To do that, the first thing was to make a constructive heuristic, resorting in 4 lists. The list of employees that are available to be assigned to a given shift. The list of employees that are currently working, so they are busy because they are effectively working and not finishing yet the shift. The list of employees that are resting, and the list of employees that are at a day off, which is not the same thing. Okay. The first thing, to be honest with you, is to make a solution that is very fast, even if it is not the highest quality solution. What we've done was employees are assigned to a order that are in the list of available employees until the minimum staff requirements met for each shift. So we know that team A will need 4 persons that speak very fluent Portuguese. Team B will need 2 Spanish employees, and so on. Okay. We assign employees to the busy after assigning a given shift, and after the shift ends, they move automatically to the list of persons that are or employees that are resting. After 11 hours, they return to the list of availables only after 11 hours because the Portuguese law demands that. The ordering of available is fixed for the entire first week period. It can change in the second part of the month. And here the priority is to assign each employee to the same shift as on the previous working day in order to promote stability. So we are always dealing with this dual metric, stability and fairness. If the staffing requirement is not met, so remaining available employees are assigned to the unfilled shifts in their current order. Obviously, after 5 consecutive days, at most, we have to assign 2 days off. In the first 2-week period, we will have to assign day off, but important is to have a scheme that is known and can be relatively random. So that's why we pick the ID, and if the ID is even, we receive 2 consecutive days off. If the ID is if we have an old ID, we receive 2 non-consecutive days off. To have a different and fairness way, we reverse this rule in the second part of the month. So, in terms of metrics, we want at Z1, as I put there, we want to maximize the shift stability, but we'll have this dual component, which is we want to maximize shift stability for one reason, and another reason is to minimize our workload, maximize our workload fairness. How? Trying to minimize the difference between employees. So we measure in the first part, we measure the percentage of times that each employee is assigned to the same shift, something that we want to promote the routine, for instance, and we want to maximize this kind of routine. In the second objective function, we want to maximize our workload fairness. How? Trying to minimize the absolute deviation of the number of non-working days assigned to each employee. Trying to put trying to maximize minimize the difference between each employee working. So that's why here we have a solution that is better if Z1 is higher, and here we have a solution that is better when Z2 is lower. After this constructive heuristic, we applied two local search algorithm. In the first one, we use the values of Z1 and try to improve these values. How? We use a neighborhood structure based on the shift swap, meaning that we have a shift swap between each two employees. And if you do that in a complete search in your neighborhood, we'll get here a local optimum. The same thing with local search LS2. In this case, we want to minimize the workload deviation. How can I do that? Using a neighborhood search related with that, swapping of one shift and one assigned day between two employees. Okay. And at this point, as I said to you, we'll have a local optimum considering the objective function Z1 for LS1 and the objective function Z2 for the second case. In terms of results, we have we tested our algorithms in 39 instances. 10 of them are real, but we have to change because we have some confidential issues. 29 randomly generated instances, and we implemented all the algorithms in C# programming language and run in a standard computer. As you can see here, our constructive heuristics can maximize can have a good quality solution in terms of stability, because we can achieve at roughly 70% of the stability. In terms of when we pick this result from the constructive heuristic and go on to local search, we can improve this value in terms of stability, and in terms of gain on our fairness, it is more important to see that we have probably 40% of improvement. This can be explained as our constructive heuristic was more devoted to Z1. As we'll see here, we can say perhaps I'm missing something, but we can see that these objectives are conflicting. So it's not clear that LS2 cannot hurt LS1, but the opposite never happens. Okay. We can see that LS1 improves Z1 in the vast majority of instances. In the cases that we have not improvements, it's the cases we analyze that cases, and they correspond to cases that are overstaffed teams. We have an average gain of 80 roughly %, peaking 34% for a case of 17 employees in a month. In the case of LS2, we can improve all instances, meaning that we can do something to improve the fairness. We have an average reduction of 28%, peaking in some cases 90%. It is important to show you that LS2 targets the same instances where LS1 had no space to improve. As I was telling you, both objectives are competing. Perhaps we need to have multi-objective perspectives in the future, because we are dealing with problems that are not convenient sometimes for this company. it's not easy to explain to this company that measuring fairness can be good for a company at the first saw. Okay. Just to finish, I don't know if I'm good with time. Just to say that all the algorithms are very fast. We have constructive heuristics lasting 0.4 seconds. Our local search, as we can see that it is a local search that search in all neighborhood with making a complete search will have up to 2 seconds to solve the problems, but they are completely they are compatible with the services that are dealing with these problems, since they use spreadsheets and they use some kind of old procedures to schedule. Okay. Just to conclude, the main gains of our work, as I was saying to you, perhaps we have to adopt an objective strategy combining these two conflicting objectives. Okay, and perhaps in the future we will have the opportunity to incorporate employees' preferences. Okay, that topic is very important, because they can motivate even more our employees in this kind of industry that are dealing with a lot of problems in terms of motivation. Okay? And analyzing other performance measures, trying to measure what is employee satisfaction in our work. Thank you so much for your time, and I'm available for your questions.
Thank you, Telmo, for your very nice presentation. Any questions? I have a question. I hope no one from the union or sindicato is here. And my question is it possible that if you optimize the number of, and optimize is tricky, if you optimize the number of employees, it will help solve some of the issues that you have to face? Namely, the number of days that they are off.
Yes. The thing that we saw in this problem is if we only look to the economic perspective, trying to optimize our schedule, in terms of employee stability is completely lost. So we have shifts that are starting today at 8, tomorrow it will be in the afternoon, and so on. Okay, so we saw that it's very complicated to show a company, okay, let's try to put all our employees starting at the same hour. Why? Because for us, it doesn't seem a problem.
Okay.
We'll go on strike.
Okay, thank you. If you have further questions, you have the opportunity in half an hour.
Thank you so
Thank
much.
you. So the next presenter is Yushi Asahiro. Go ahead. And if you need to have water there.
Oh, thanks.
Good morning. I'm Yuichi Asahiro from Japan, and the title of my talk is Approximability of the Maximum Two-Click Problem for Photographs. This is a joint work with Miyano and Nakamura, also from Japan. Our paper is about the theory and does not include any experimental results. Anyway. Okay, this is the outline of my talk. First, I will introduce the problem max to click, and then summarize some known and obtained new results. And if I have a time, I will show you some main ideas to obtain new results. Go. We start with the problem. And the problem max to click is a generalization of the well-known problem max click, or max click. Here, the input is an unweighted and undirected graph. And then the max click problem is to find a maximum click in the input graph. Here, the maximum, here, a subgraph is a click if the distance between any two vertices is 1 in the subgraph. It is also called a complete graph. If you think about this graph, and if you regard the vertex as a person, and edge, if your edges represent the friendship, the complete click or complete graph represents some group of complete friendship. Then there is another problem called max to click. This is a generalization of the click problem in terms of distance. The problem max to click is to find a maximum 2 click. Here, a graph is a 2 click if the distance between any two vertices is at most 2, which in practice it implies that we allow the group as a friend of friends. Yeah, this is a generalization. So for this graph, the red part is a maximum click, which has 3 vertices. But for 2 click, the blue part is a maximum 2 click here. But there is one thing to take care of. Here, if you look 2 vertices B and E, the distance between B and E is 2 in the entire graph. But if you look only the blue part, its distance is 3. So we think the distance here in the entire graph, entire input graph. So this is the point. Anyway, so let me summarize some results. Actually, the maximum click, max click, and max 2 click are NP hard. So it is very difficult to design polynomial time exact algorithms. So one direction of research is polynomial time approximation. Here, if algorithm A outputs a solution satisfying this inequality, which is the optimal size over the size obtained by the algorithm is at most sigma, for any input graph, then it is a sigma approximation algorithm. Or sigma is called an approximation ratio. Here, for example, pure approximation algorithm outputs a solution of size at least half of the optimal solution for any input. Then for this line of research, we would like to try to show some approximability and inapproximability. For approximability, we try to show some existence of polynomial time sigma approximation algorithm for some small sigma. And as for inapproximability, we try to show non-existence of polynomial time sigma approximation algorithm for some large sigma under the assumption that P is not equal to NP. So this table shows known results for general graphs. Actually, okay, let me see that here for maximum. There is an approximation algorithm with approximation ratio of square root of n, and we cannot have any approximation algorithm with ratio slightly smaller than cubic square root of n. This implies that n here n is the number of vertices, and each long represents any positive instant. So this means that we cannot have approximation algorithm with ratio n to the 0.49999 or something like that. So in polynomial sense, we have very tight approximability and inapproximability for these two problems. So As usual step, we sometimes restrict the input to some subclasses of graphs. So in this talk, I'm focusing on the caudal and the split graphs. The definitions of these graph classes will be explained later, but here, one property of these graph classes is that split graph is a subgraph of caudal graphs, and caudal graphs is subclass of general graphs. So for max Greek, it is known that it is polynomial time solvable for caudal graphs and split graphs. But for max Greek, it's unknown. So this time we tried to fill this table. Then we obtained these results. We designed some cubic root of n approximation algorithm for caudal graphs, and for split graphs we showed n to 1/3 minus epsilon in approximability. Actually, the split graph is a subclass of caudal graph, so this in approximability is transferred to the caudal graphs, and this approximability is also transferred to the split graph. So we actually obtained some very tight approximability and in approximability for these graph classes. Okay, let me talk about the definition of graph classes. A graph is caudal if every cycle of length at least 4 has a chord. Here, chord is an edge connecting between two non-consecutive vertices. For example, if you look at this cycle of length 4 with brackages, then one chord is like this letter H. This connects the non-consecutive two vertices. Then for cycle of length 5, well, yeah, that's okay. So, my example of code is like this red figure. So, but here, still we have cycle of length 4 with 3 black edges and 1 red edge. So, in practice, we need one more chord here, but I omitted it. Anyway, this is a caudal. And a graph is split if vertices partitioned into a creek and an independent. Creek is this part, and the independent set is a set of vertices in which every between there is no edge between any two vertices in the independence. So this graph is a split graph, and the upper part is a creek, and the bottom part is the independent set. So we can partition the vertices like this figure. So this is a split graph. So, okay, let me explain some ideas to obtain approximability for caudal graphs. The proof flow is as follows. First, we consider an optimal set of vertices of maximum 2 creek in a caudal graph. Then, one observation is that if we look at some vertex R in the optimal set, the optimal set must be a subset of R plus N1 R plus N2 R here. N1 R is the set of vertices of distance 1 from R, and N2 R is those of distance 2 from R. Since we are now considering a 2 creek, in which every 2 vertices have distance at most 2, so the optimal set must be inside this area. So, but like this figure, here is R and it's R, and that is NR and it's R. So the black point represents a solution. So the optimal set must be a subset of this area. So we showed some main lemma shows that intersection of N2R and optimal set has size at most about 4 delta to the 3/2. Yeah, this is the main lemma. Then here, delta is the maximum degree, and degree is the number of edges incident to a vertex. So then after that, we consider a very simple algorithm which outputs a vertex d of degree delta, which already exists, and its neighbor vertices. So the output is like a tree of height 1, which is called a star graph, and it is clearly it is clear that distance between any two vertices is 2, at most 2. So this simple algorithm outputs a 2-click of size delta plus 1. Okay, so then the analysis of an approximation ratio is like this. We observe that some upper bound can be shown. This is not so difficult, but here, n is the number of vertices, which is clearly it's a trivial bound of optimal solution. So the another bound comes from the main number, because the main number shows that the intersection of N2R and optimal solutions like this, and we before we observe that the optimal solution must be a subset of this set. So the size of an optimal set must be 1 plus 1 corresponds to R, and delta, which is intersection of N1R and this upper bound of this. And the main lemma gives this bound. So we know that the upper bound of an optimal solution is like this. So the analysis is as follows. When the maximum degree is at least n to the 2/3, optimal size over the algorithm size, or the solution size, is at most n over delta plus 1, which here we use this one here. And this corresponds to the cubic root of n. And when delta is smaller than n to the 2/3, we use another bound here. So the opt over a is at most this value, which is equal to delta to the square root of delta. Now delta is smaller than n to the 2/3, so this corresponds to the n cubic root of n. This is the analysis. I have a few minutes, I think.
Yeah, 5 more.
Oh, yeah. So this is the idea of showing the main lemma, estimation of the intersection of N2R and S. This figure shows some 2 vertices in the intersection of N2R and S, U and V. So if we look at R and N1R and N2R, the distance between these U and V seems larger than 2. So we need some other edges to satisfy the distance condition. So actually, there are many cases to enumerate, but here I showed 3 representative cases. Yeah, if we have an edge between U and V, it makes the distance 1, so it's good. Or if we have this edge, it makes the distance is 2, so this is also good. And or this is the most complicated case, but there is a path of length 2 between U and V. So there are some cases to satisfy the distance condition. So the point here is that now we are thinking of caudal graphs. So what was caudal? A graph is caudal if every cycle of length at least 4 has a chord. So looking at the left figure, this is cycle length 5, so we need a code. So there must be some edge like this red one. And for this, okay, we need some edge here, but we just want an edge between N1R and N2R, so we just skip this case. And for this one, we also has some code like this figure. Then the strategy of the proof is the assignment of the pair UV to the edge between N1R and N2R. So in this case, I assign the pair UV to this red edge, or this edge, or this red edge. This is the strategy. Then investigating all cases, we observe that at most 8 delta pairs can be assigned to one edge between N1R and N2R. Then we know that the number of edges between N1R and N2R is a delta square, because the delta is the maximum degree. So we see that the number of pairs of vertices in the intersection of N2R and S must be at most 8 delta times delta square, because one edge can have 8 delta pairs. So this formula gives the desired bound. This is mean name. Okay, let me skip this part. Let me conclude. We obtained new results for maximum to click problems for order graphs and split graphs. Actually, there is another very similar problem called max to crowd, and the same idea works for this another problem, max to crowd. And so we filled this table. And as future topics, it must be interesting to investigate complexities of these problems for, say, bipartite graphs and other graph classes, and so on. Thank you very much for your attention.
What? If somewhere out there have questions? Well, yeah. We can ask questions in the coffee break, and we will follow to the final presentation. Thank you again.
Thank you very much.
And Eligius will be our last presenter of this session.
See, we can wake this up with a mouse for elder people.
Yeah.
So it's wonderful to be here in Braga, where you've been many times before. Now, oh, here we are. Okay. Let's try to wake up faster. Yep, there we are. I go to a control. Oh, it should work now. Okay, guys. So I was telling the presenters yesterday that you're online, so there can be thousands of people listening. This morning I realized that YouTube also says, there are 2 people listening to you. Okay, so it's not exactly the same. So I come with a story about battery storage management, and I will tell you first the motivation. So this is a cooperation we have with Ana Rocha and Pablito, Pablito. And the thesis of Ana Rocha was about augmented Lagrangians. And Pablito's thesis was about linear programming. So we said, okay, we combine that. So for 2 years, last year, we did a presentation. We were playing around with augmented Lagrangians that we use for solving linear programming, actually for a special case. So what we did over there was, what Aisha was also saying, okay, this theory, now is this really working? So what we did was using benchmark problems to test whether things are working, variance of the algorithm, and see how things are working. Okay, I'll show you the algorithm, and I do a little bit of story about battery management and why are we doing realistic cases. because Anna was visiting us, and the provider of the funds said, no, you have to do an industrial application. So it's to show that it makes sense what you're investigating. So at the end of our stay in October, I said, oh, I have to invent something. So I was inspired by some story, and I made a story about battery management, which is very accurate. I mean, it's not, I invented it, but it's something realistic, okay? This is a little bit story. So if you look at the literature, then there's a lot of stories about we are dealing with the energy transition, and now you say your neighbor, does this work? You bought the battery, does this really work? No? Okay, it's very funny. So the neighbor, of course, you live in the, no, you're not living in the house, okay. So if you live in the house, you are not there. Okay, you have the solar panels on your roof, of course. No? When you're in Europe, that is for the richer people. No, so I'm rich. I used to buy solar panels. I don't have them anymore in another house. But this story, no. So in this energy transition, now there comes a story about batteries. So we can. It would be good if the world mitigates the effect of the vibes we have in generating the energy over the day by storing the energy in batteries. Okay, so this is the story. So this is the picture I made. You can also see when we are doing this investigation. So my contract says the price of the electricity is varying during the day. Okay. Okay, it's not because I invented it. It was invented by European Union. Okay, so European Union said, well, when the energy crisis started, we have to take care that people turn on the washing machine when the price is low. No, but that stabilizes the system. This is not the idea. No, we all know that something went wrong even in Spain last year, so we have to really stabilize the system. Okay. So the idea is the following, that the price is varying during the day, right? So what do you have to do with the battery? You just store it when it's cheap and you sell it when it's expensive, okay? With my contract, I think I cannot do that, but usually people who have solar panels, they have a system where they can sell back, okay? So I repeat, I invented this story, no, more or less. And then I was surprised because in April I arrived at the house of my brother and he says, no, since January, this battery, so his house is of course completely covered with solar panels. Now we have this new battery over there. And I see my sister-in-law 2 weeks ago proudly saying, we're gaining €7 today by selling the electricity. So if I read the news about it, then usually people say it's not really profitable, but it's a nice idea that we stabilize the system. For them, it may be profitable. I will also define why this is going on, okay? So what we were looking for was for an easy problem where we can test our ideas we did before. So we wanted a sparse problem, an LP problem, where we can do this augmented Lagrangian story we did before and compare that with using the simplex method. Okay, so this is what we wanted to do. And the story is nice because we have a realistic story that I realized was, so this is the typical way I like to write my LP programs for the last 40 years now. So you want to distinguish the data, the variables, and your indices, which in this case is relatively easy because I just have a dynamic system. The question is whether you should use LP for this, but we were playing around with linear programming. No? So what you typically have is the amount you have stored and you're buying and you're selling every day, and you have to design that, okay? Another story I have to say that because one of the referees started, this is not realistic. And how do you know? The price. We know the prices, at least in Spain. I know the prices at 9 o'clock in the evening for the next day, for each slot. So slot is 1 hour. In the Netherlands or Europe is already changing to 50-minute slots because that's more efficient. Okay, so or it's better for the system. Let's say it like that. As a consumer, it's not necessarily better. No? Okay, So we have slots of 1 hour. That means the potential that I have in kilowatt that translates easy to kilowatt hour now. But they also have maxima on what I can store and what I can get from my battery and what I can put into my battery. Usually what I can put into my battery goes a little bit slower, no? Okay. So I have a relatively easy linear program which only is based on a balance equation. What I have in the battery is what I had before minus what went out, and plus what came in, something like that. That's it, right? So the profit I'm making is if I sell at the same price, right? There's something in between. You cannot do that in Spain, but in the Netherlands, up to 1st of January, this is still the case. You can sell for the price you bought. So that's really very profitable, no? But okay, then we made something in between to say, okay, what you're selling, that's you get less money for what you sell than what you buy. Okay? Otherwise, the solution would be very easy, no? Okay. So what we typically now have in linear programming terms is, good morning, what we have in linear programming terms is a maximum on your decision variables. No? So we're really at your favorite, obviously, we're really at your favorite story because this is linear programming. Friend comes in, so, okay. I'll show that. No? Okay. Repeat. Linear programming with data, okay? Right? Okay. So now I'm moving a little bit in the direction of the investigation we were doing. Because what you would do is to take this guy, you throw it into games, not do something else. No, you throw it in your solver, or in this case, in your MATLAB solver, and something is coming out. No, okay. Our investigation was dealing with augmented Lagrange. So what's that story? So you have this linear term on your decision variables, and then you have, I will explain that more in the presentation this afternoon. Then you have D stands for, direction over here. No, okay, dangerous. Right. Oh, you already showed me. I shouldn't. Don't touch the screen. Don't touch the screen. So we have my Lagrange multipliers over here. Favorite story too. Okay. And the feasibility is defined by C is AY in this story. Okay. Often we use an notation. It's not important, right? So feasibility means that you have a feasible solution, right? Okay. So what you do in augmented Lagrangian is you take Lagrange multipliers and a penalty. Okay. Over here I have something which is called a quadratic penalty. Okay. Important. Don't lose the story, right? I give a penalty, I give this Lagrange multipliers, I optimize this quadratic function as you see, okay? Well, if you think about it. And I do this several times. So I optimize this until I can converge it. So yeah, I have a complete, beautiful, our favorite LaTeX algorithm, of course, where this is what we are doing, okay? So you solve the problem. No, find the minimum of the Lagrangian, right? You update the Lagrange multipliers. That means if you're over, then you penalize. Less, you release the value of the Lagrange multiplier, and you're going to, in this case, you can do that in several ways, but in this algorithm, you're going to increase the penalty value. Okay. Up to you have convergence, something like that. So what's the surprising question? How is this going to work if you compare that to linear programming? No? Because having taught linear programming for 20 years now, throwing simplex tableaus at my students, let's say it like that, okay, you know how that works, but this works slightly different, no? So we can play around now with the data we have. Now we have realistic data. No? We can play around with this setting. So if you look at the A matrix, it's funny. So we make this picture of the balance equations. You know. So The only thing you have to take care of, I was not very explicit about that, is that at the end of the day, you have the same amount as at the beginning of the day. Neither that's necessary, but okay, it's to have a cyclic way of thinking, right? So at the end of the day, I try to have the same amount, and that gives one of the equations, okay? Now, let's do semi-realistic data, no? So what's semi-realistic? This is my contract, no? I can get 4.6 kilowatt out of my system, okay? Otherwise, right? So you see the variation of the prices. So when the price is low, I tell my wife, of course, plug in the car, plug in. Right. Okay, so we see this variation. We see this is my contract, and then in my story, I do a maximum discharge, which is less than you can put into the battery. Okay, right, and then we do an imaginary price difference. Otherwise, you get very strange answers. Okay, and in this case, I want at the end of the day, I want to have 15 kilowatt hour again in my battery. No, so I have this realistic data, and my question was, how is this going to behave? Huh? Right? So luckily, I'm working with Anna, so she's very good at doing experiments, right? So you have to set some initialization, and what we are doing over here. We usually have discussion about this, about the accuracy epsilon, that they talk about square root of 2 in the power minus 52, where I say it is 2 in the power minus 26 now. Okay, good. So in my next story, I'm going to focus on that. What we did over here, and also in our former experiment, is that we use F-min common of not one. Basically, this is ugly. But why is this ugly? F-min common is to solve anything with nonlinear, objective, and constraints. At the moment, I don't have that. Actually, convex quadratic function. I'll come back to that in the afternoon. No? Now, what was essential, so that I found with Anna, if you use this FMICOM, you use the active set solver in this case, because basically your solution, I'll show the solution in a moment, will be pretty bang bang. So you will be at the upper bound or lower bound basically. And because we have this story, we can put the gradient analytically. Now that's fun, right? It's usually this more. So this is the typical contribution also of Pablito. He likes to say that we have so many digits over there. Okay. Then they usually say that these are cents. Okay, this is it now. Now at the moment they are euros. Okay. Now I realize these are euros. So this for my sister-in-law. Now she gave 2 euros this day with on the 31 of October. I'm saying that. So why was he doing this 2 weeks ago? I don't know you noticed, but there existed something which was a heat wave. What happened in the heat wave? At least in Spain, I've shown you this picture of the prices which vary between 3 cents on Sunday, plug in, no, up to 30 cents at the afternoon. So what happened last week? Last week I've seen in Spain a price of 89 cents at 9 o'clock in the evening. Well, why is that the case? Because that people plug in the air conditioner. Okay, so you get very high prices. So the story is, if you have more variation, then this battery makes more sense. No? Okay, so that's the absolute value you see over here. What are the surprises for me? I wanted to see this now. Okay, how does this behave? Okay, I wanted to know this. Now, how many iterations does this augmented Lagrangian do? This is not an effectiveness story, but this is an effectiveness story, not an efficiency story. I mean, it doesn't say anything about pricing, but I was very curious how fast this convergence goes for realistic cases. As we said, we use benchmark things in our earlier study. Okay, let's try to round off. I give you this picture of battery management. Give you a slide picture of the augmented Lagrangian. What's going on? Okay, so the the typical pictures that come out, perhaps I should stress that, is first have to get used to this now, okay? So I have in blue, I have the amount I bought from the grid, and in purple, I have the amount I sold to the grid. Now you see typically that things are up and down. So this is called the bang-bang process, no? So if you're doing a dynamic process, and then some values are in between. Yeah? It's very, very funny. So basically you're charging or discharging on the level of an hour. In dynamic programming, where we do milliseconds or something like that, we can also have this. But this is the realistic situation of doing 24 slots on a day and what's going on. So in the bubbles over here, you see the storage. No, you see that I've reached a maximum over here, and then in the end, I have to use it in the evening because the price is going up, and then you have to charge again. Take care that you reach the 15 kilowatt hour in the end. No? So this is the pictures that are coming out. I was very enthusiastic to get these pictures out because this is at least the kind of realistic story of how a system would behave. No? So of course the system of my brother doesn't. He calculates also the thing before. It doesn't use linear programming. So you have to find this is provided by the company, no? Something like that. I wanted to know how this would work for if I do a linear programming over here, okay? So this is, the slides were written by Anna, so there's a lot of text over here. I'm not Iberian, so I use less text, or I'm less good with text, let's say it like that. So it summarizes a little bit what we have been doing, you know? So we've been giving the numerical experiments and see what's going on, okay? So also we discussed about it because one of the referees was talking about price forecast, but I'm not worried about price forecast. I know the prices in the evening. What's the non-realistic part? For my brother, the realistic part, no? Okay, that he's generating energy and he is also using energy, and the amount you generate and the amount you use, that can be considered stochastic, okay? If you want to talk about stochasticity, it's over there. But you can also make a forecast over there, what you're going to do the next day. And even you can influence what you're going to do the next day because you switch on the washing machine or you plug in the electric car. No? So that's fine. So I think this is, when I wrote down the model, this was the first thing I was thinking. Okay, it's completely realistic, but okay. But it gives the high line. Now, what was important for us is also to have the backup of the literature. So we were reading about battery systems, and it refers to our things. Okay, so this is the last slide. It ends in time before the coffee and over here. Thank you for your attention.
Any questions?
Nobody buys battery?
So if anyone has questions, we have coffee break now. We can address issues during coffee.
Okay.
Thank you all. See you in the afternoon.
Just beautiful, huh?
Like,
Vou cumprimentar em breve.
E o das boleias chegou e, portanto, comer bem.
É os problemas das conferências de Portugal.
Pois é, mas é mesmo. Mas tu fizeste bem. E esta ficar a semana toda.
Olha, João, obrigado. Depois vou dizer, se eu souber novidades, vou dizer, está bem? Mas não está fácil de ver. Obrigado. Olha, volta depois para jantar. Olha, isso é que era. Anda lá. É só verdade. Então, eu não via. Os tempos que nós somos verdade. É verdade. Olha, eu este ano eu vou dizer, eu vou ao Optimization este ano. Eu vi que tinha 3 sessões de sessões mesmo, não apenas apresentações, mas é só uma. É uma e não é só isso. Mas está tudo o pessoal do software, o source tem uma plataforma. Sim, eles também têm não tem investigação. Não necessariamente na tua área, mas juntar as duas coisas é que é interessante.
Nós temos um projeto por acaso agora, semana passada,
Espero que este ano para ainda mais pois vai. Não, mas estou a dizer este ano, a informação do Rio e isto podia ser
mas isso depois também tem implementado
enfim, vamos ao coffee break, meu caro.
Coffee break, let's go. I'm already selling. I have to make companies about selling.
Let's go. This was blown out last year in Spain. Also in Portugal.
Yeah, for self-consumption, it's profitable, but not for sale. In our faculty, we have solar panels, we solar